Good afternoon, everyone. Uh, Today I will be talking about low density parity check code from Secantech Inc. So Secantech provides a large base of forward error correcting codes, which include BCH, which are binary, Reed Solomon, which are query, like 2 bits, 3 bits, 8 bits, 16 bits, symbol sizes. Then there is fire code fake, which uses 2 or 3 polynomials. Then there is Ldpc binary query and polar codes, and AES is for encryption decryption with different key sizes, and the GCM for AES mode, and SHA for hash authentication with HMAC and without HMAC. And we also have the scrambler, descrambler. So Ldpc is used mostly in 5G, which is the main use case for Ldpc, but it is also used in WiMAX, DVBS2, 802.11n, 802.3ca, and other BCH equivalent Ldpc A-list files with parity check codes. So as long as a A-list file or a PCHK or the parity check matrix is available, the decoder can be easily generated from our scripts. So whenever there is a transmitter and the transmitter sends data to the receiver, it goes through a channel, and the channel could be from satellite to the dish or from tower to the cell phone. Then in that case, there is an error that is introduced in the data transmission. The error probability is P, and the percentage error probability is 1 minus P by P. So if a high or a 1 is transmitted, then the bit received on the receiver side has a probability of minus percentage probability. And if it is a 0, then it is a percentage probability. And if we know that the bit was not transmitted, then the percentage probability is 0. This is actually in the BPSK, where the bit received has a differential polarity. So in Ldpc, mostly it is a quasi-cyclic Ldpc codes where there is, let's say, if there is a lifting factor of 4, the Z has a factor of 4, then there is a 4 by 4 matrix with ones as shown. And if the quasi-cyclic value is 0, then it is a identity matrix. If the quasi-cyclic value is 1, then all the rows are shifted, circular shifted by 1. And if the quasi-cyclic value is -1, then there are all zeros. As it can be seen, there are more number of zeros than ones, so there is a low density. So this is the diagram of the matrix. On the left, there is a m by n matrix, where m is the number of rows and n is the number of columns. And in the middle, there is a code word. The code word is n bits. N bits, and the number of columns is 1. And on the right, it is a m bit matrix with number of rows as m and number of columns as 1. These are the check nodes. So to begin with, the message is known. The message is from 0 to n minus m minus n minus 1. So n minus m are the bits of the message, which get multiplied, will get multiplied by the parity check matrix on the left. But at that time, the parity bits are not known. So in that case, the parity bits are calculated in such a way that the check nodes on the right, which is m by 1, are all zeros. So when that happens, when the code word is transmitted on the the receiver side, the receiver knows that the check nodes have to be 0, and it has to adjust the code in such a way that the check nodes are 0, so that the code word is almost error-free. So what is delivered as part of the LDPC code is ldpc.so file, which is the encoder, decoder, C files, then the parser file, which is actually parsing the output from the ldpc.so when we run through one of the example. So if we have a different A-list file or a parity check matrix file, then it will generate different encoder and decoder using these parser files. Then there is a make file to run the test. So there is just one simple test which will run and make sure that converges. And this test can be run with multiple, like the probability on the channel. And if A-list files are provided, we'll use the A-list files, or if A-list files are needed, there are a lot of A-list files in the package that can be used. Then there is a script to convert from PCHK file to A-list file and vice versa. So PCHK file will have the whole parity check matrix in ones and zeros, and the size of the file is too big. But to consolidate all the ones which are low densities, that is used in the A-list files. Then the system Verilog RTL code will be generated for the application that is targeted, and it will have all the encoder, decoder, syndrome calculator, and Hamming distance calculator. And there will be a C code. The test will run actually on the C code and the system Verilog files and make sure that they are consistent with each other. So the decoder takes as few as 5 cycles per iteration. This is like without having pipeline stages for the mux trees that are present in each of the iterations. So it is very fast, and it has a lesser number of iterations as it uses sum product method, and it does not use the min sum method. The min sum method approximately takes about 20% more of the iterations. So for a code word, the decoder can finish like in 8 into 5. 8 is the number of iterations and 5 is the number of clocks that it needs. So in 40 clocks, it can complete. So there are different logic. There is a different logic for every A-list file, making it parallel, and we can have more encoding and decoding running in parallel. So the decoder options are, it will come with a CRC generator and rate matching, puncturing and shortening. It has high data rate and throughput, and configurable for any of the A-list files. And it has auto terminate on divergence. Let's say the error on the channel is too high and it cannot converge, then it will terminate after a few iterations. So there is a m by n matrix multiplied by n by 1 matrix, that is code word, which will give the syndrome which is m by 1. And the encoder has a pn n. The encoder needs to generate the parities of m parities, which will start from n minus m column to the n column. So that is like m parity bits. So here is the example of 5G. The 5G initial first 2 star Z is the lifting factor. So the first 0 to 2 star Z bits are punctured, like they are not transmitted. and they are unknown on the receiver side. So the value is percentage probability is 0. Then from 2Z to A are the actual message bits that are transmitted, and they are received on the receive side, maybe with errors or without errors. Then from A to N minus 1, these bits are assumed to be 0, so that we don't want to make it unknown, but we want to make it assumed to be 0. And then from N minus M to some parity bits, total bits sent are E. So all these bits are sent to the receiver side. And from this E minus A minus 2 star Z to N, these bits are punctured. So these are the parity bits which are punctured. So total transmitted bits are E and total message bits are A, but the total message bits sent are A minus 2 star Z. And so finally, the efficiency of the channel or the rate of the channel comes out to be A by E star 100%. So in the 5G, the BG1 has 20, like it has 46 rows and 22 message columns and 46 parity columns, and it has 42 rows and 10 message columns and 42 parity columns. So total the rate comes out to be 0.32 for basecraft 1 and 0.19 for basecraft 2. But it has 51 of these matrices which are actually different LDPC lifting factors. So it has a total of 51 plus 51, that is 102 matrices, and there will be each encoder and decoder generated for each of the matrix. So what's in the encoder? The encoder the C code will read in the parity check matrix, and then it will read in the C program will read in the A-list files, and the parity check matrix will be converted to A-list, and that will be used for generating the encoder. The encoder output is the parity bits. So this is the system Verilog encoder. The encoder takes in message bits, which are N minus M, and it gives out the parity bits, which are M. Once the parity bits and the message bits are known, then it is the N code word. The code word will go to the syndrome calculator, and the syndrome calculator will make sure that the check bits are 0. So in 5G parity check matrix, it is arranged in such a way that you can see I have noted down 5 or 6 of these rows. And the first row, there is P0, P1 on the parity check. And on the second row, there is P1, P2. And on the third row, there is P0, P2, P3. And on the third or the fourth row, there is P0 and P3. So now for 5G, what is done is all these 4 rows are added to get XORed together. Once they are XORed, the P1 gets cancelled, P2 gets cancelled, P3 gets cancelled, and 2 of the P0s get cancelled, and what is left is P0. So final result is P0. Once that is known, the P0 is known, then P1 is known, and after P1 is known, it is calculating the P2, and then P0 and P2 are known, then it is calculating the P3. And once that is done, then it goes to the P4, the row 4 or the 5th, and it is just the identity matrix. So P4 is calculated straight away from the message bits, and then P5 is calculated from the message bits. So this is how the 5G encoder is implemented. For DVBS2, there are again 6 or 7 of these rows that are listed down. In the first row, there is P0. Second row, there is P0 and P1. And third row, there is P1 and P2. So from the first row, we can calculate P0. Once P0 is known, from the second row, we can calculate P1. Once P1 is known, we can calculate P2. And from P2, we can calculate P3 and so on. So for Ldpc decoder, input is the parity check matrix. The parity check matrix is converted to the A-list files. The C program reads it and generates log files. So while calculating the encoding and decoding, it generates log files. The log files are then parsed in C. There is a C parser which is reading all these log files and then generating system Verilog code for the decoder. So this makes it like very convenient to reconstruct a decoder from any of the A-list files, as it only needs the machine time. And then the decoder takes in 5 cycles per iteration, so it is very fast. But the mux tree is pretty big, I would say, and it could need some pipelining as we put it into some technologies. So then it can have pipeline stages in each of the iterations, but still it will remain very fast. Then check at the end of iteration for convergence and divergence. So it will calculate the Hamming distance, and once the Hamming distance is known, it will know whether it is actually converging or diverging. And the input coming in is 3-state value. So BPSK low has a value of 1, high has a value of 0, and unknown has a value of 0. High has a value of 3, and unknown has a value of 0. So this is the diagram of the decoder. So in this diagram, the decoder is actually doing iterations 1, 2, 3, and you can do as many iterations as needed. You can do 50, 100 iterations, but every iteration, it will calculate the syndrome and will check whether the syndrome is 0, and by calculating this, by comparing it with the syndrome bits and the 0 bits with using the Hamming distance calculator, and that will actually circulate through into the decoder. So this is the, I would say, this is the sum product algorithm that is implemented, and I would not go too much into the details, but this is how it is implemented, and this is how all the float to fix to float is done, and that is optimized in the system Verilog. So thank you, and have a good day.